Power Series, Video 2. In Video 1, we established this convergence theorem. Let's look at the three different cases. Case 1 was that you only have convergence at the center, and then everywhere else, the series diverges. Case 2 was that you have convergence everywhere. Case 3 was the in-between case, where within R of the center, the series converges, but then more than R away from the center, the series diverges. Good. Let's use these notions to make definitions for an interval and radius of convergence. So here we're making a definition for interval of convergence and radius of convergence. Let's bring back those three interval pictures. So on the first one, the amount that we can stray away from the center is 0. In the second case, the amount that we can stray away from the center is infinite. And then in the third case, the amount that we can stray away from the center is non-zero and finite. These three pictures correspond with the three different possible outcomes for the convergence of a power series. Excellent. Let's do some examples of this application. Here we have a power series. Note that the center is A equaling 1. We want to find the interval and radius of convergence. First made a statement that the center is A equal 1. So we're looking to find how far away from that center can we stray with x's and still have convergence. Trying to find the radius, and then once we have that radius, then indicating this interval. Now, the naive approach is just looking at this and seeing that we are translating the geometric summation of x to the n to the right by 1. Let's see that that's actually the case. The way that we go about it is, well, let's first make a definition of what the terms of the associated sequence are, and then use the ratio test. And remember, the ratio test is a test for absolute convergence. It's the next term over the current term. This guy raised to the x minus 1 raised to the n plus 1 is the binomial raised to the n times one more copy of the binomial, placed over the current term a sub n, quick cancellation, bring the remaining term with absolutes around it down, and then limit as n goes to infinity, and you just get absolute of x minus 1 as n tends to infinity. We're doing the ratio test, and in the ratio test, you want the row quantity to be less than 1, strictly less than 1, and we're finding our row quantity to be the absolute of x minus 1. Okay, so you can look at this and you can see that x's, how far can they stray from 1? They can only stray a unit from 1, a unit from A. In other words, that is our radius of convergence. Going back to the picture, we now know that we can be at most, or within 1 of the center. We don't know if we can actually be 1 from the center. So we want to check, well, what if we are exactly 1 away from the center? So 1 below, that'd be 0, and 1 above, that'd be 2. So you have to check each of these. I'm calling that a test. You test, do we have convergence at 0? Test, do we have convergence at 2? Remembering that a sub n is x minus 1 raised to the n, plug in 0, you'll get negative 1 to the n. Plug in 2, you'll get 1. Look at how those behave in the limit. Neither of them goes to 0 as n goes to infinity. Thus, we can apply the divergence test, and we include neither in the interval of convergence. Good. Let's summarize what we found. We found that the radius is 1, and by doing the testing on the endpoints, that the interval of convergence is open at 0 up to open at 2. Fantastic. Let's try another. Okay, so now let's make it a little bit more interesting with an n factorial competing against the exponential in the numerator. All right, well, it's a computation. It's a ratio test. Make sure we can see what our a sub n's are. So this guy here is a sub n plus 1. Denominator, you're going to need an n plus 1 quantity factorial. Peel off the binomial n plus 1. Save an n factorial in anticipation of a cancellation. Numerator, we did that in the previous slide. Dividing by a sub n, the same thing as multiplying by its reciprocal. Make cancellations. Come up with x plus n in absolute. N plus 1 is positive. You don't need the absolutes on it. No matter what you choose for x, no matter how large you make x, adding in 1 makes it a tiny bit larger if x is positive. You're always going to be able to find an n value which outstrips the numerator. Thus, this goes to 0 as n goes to infinity. This is the ratio test. We're getting a rho. Rho equaling 0 is telling you that this will always converge. So the n factorial in the denominator helps tremendously. You can plug whatever you like into the numerator. All right, summarize that. We found that we can plug any x in, so we can move away from, what's the center here? Negative 1. We can move an infinite amount away from negative 1 and still have convergence, so we get the interval of convergence is the entire real line. Beautiful. Let's do one more. All right, so now we're playing around. N factorial was in the bottom. Let's put it in the top. And how is that going to affect things? Let's find out. Okay. So ratio test. We have the current term. And then the next term. Make cancellations. Clean that up. And same idea, no matter how small you make x, well, unless x is negative 1, so other than negative 1, this will go to infinity as n goes to infinity. And then what's going on, again, aside from x being the center, what's going on? You're getting rho equaling infinity. Rho equaling infinity in the ratio test tells you you diverge. Therefore, the interval of convergence is only the center. Oh, and here's a nice challenge problem. In this challenge problem, how will this 1/3 coefficient on x affect the interval of convergence? How will it affect the radius of convergence? Find out. Challenge yourself. Excellent.